Hello again, this is Professor Roman. Let's continue the lecture series on Transition to Advanced Mathematics. We have been talking about proof techniques, and I outlined for you the basic proof technique templates. So let's look now at more detail at these templates and also examples. Before I start, though, I want to point out that the examples and exercises in the book haven't exactly been chosen, with a few exceptions, for their important mathematical content. Some of the theorems are, well, I guess to be blunt, a little boring. But the point is not the content of the theorems, except in a couple of cases. It is more the construction of the proofs. The direct proof template here works as follows. Here's an example. If x and y are real numbers for which x is less than -1 and y is greater than 2, then the distance from the point xy to the point 1, -2 in the plane is greater than 4. Just as a thinking out loud matter, the conclusion of the theorem should immediately put us in mind of the distance formula. The hypotheses are not too exciting, x less than -1, y greater than 2. So we go to the conclusion, say, aha, we're going to need the distance formula. So we write that out. The distance between these 2 points, which I'll call d, is this square root. And then, so we must show that d is greater than 4. Now the proof comes down to some simple algebra with inequalities. Looking at this formula, we can see what to do with the hypotheses. X less than -1, we need an x minus 1, so we'll subtract 1 from both sides. X minus 1 is less than -2. We're going to need this quantity squared, so we square these. Now, both of these are negative, because -2 is negative, so when we square, it flips the sense of the inequality. X minus 1 quantity squared greater than 4. Similarly, we start with our hypothesis y greater than 2. We need y plus 2 quantity squared, so add 2 to both sides. Now everything here, both sides are positive. When we square, the sense of the inequality does not change. And so this quantity, y plus 2 squared, is greater than 16. Therefore, d is greater than the square root of 4 plus 16, square root of 20, which is a number greater than 4. And that is the proof. Next example, if a and b are positive real numbers for which a is less than b, then a squared is less than b squared. This is my thinking out loud here. It's in black for some reason. I guess I messed that up. But in thinking about how to construct the proof, we might think, well, a direct jump from a less than b to a squared less than b squared is a little vague. We can't just simply square both sides, because we don't know whether that's going to require a change in the sense of the inequality. Okay, so the direct path from here to here is a little vague. And this illustrates an important point too. Be careful not to jump to any incorrect conclusions. Think about every step you make in a proof and ask yourself, is this really mathematically correct, or am I making an error? It'll save agony in the long run. If you get through a good portion of a proof, you get to the end, you get stuck, and you have to go back and reread what you've done, looking for errors, they're going to be a lot harder to spot than if you do that error searching in real time. Every time you write a piece of mathematics, a sentence or an equation, ask yourself, is this really true? After a while, you won't have to do that very often, but sometimes you will write something and it might bother you a little bit. You might have to go back and think a little bit more. And hopefully it is true, but sometimes it won't be. In any case, starting with A less than B is not very inspirational. So again, we will turn to the conclusion, A squared less than B squared. So here is how the proof might start after some soul searching here. The conclusion, A squared less than B squared, can be written in this form, and factoring gives this. Okay. So it is sufficient for the proof to show that this product is positive. But this will hold if and only if both factors are positive or both factors are negative. Now that's not something that you would, I would classify as thinking out loud. That's a good sentence to put in the proof. Okay? But since A and B are positive, and that's by assumption, we know that B plus A is positive. Also, the assumption that A is less than B implies that B minus A is positive. Therefore, both factors on the left side of 410, numbered equation, or inequality, are positive, and so 410 holds. Okay. Next example. If x is a real number, then negative absolute x is less than or equal to x is less than or equal to absolute x. Dealing with absolute values often requires considering cases. So that's actually a sentence that might be thinking out loud. Now, I've continued this by saying, for the record, we have, and here's the definition of absolute value. That could probably be left out. If your readers don't know what the definition of absolute value is, they have bigger problems than reading your proofs. But it does bring up another point. When you write proofs, you need to think about who your audience is. Okay? As a student, you will write proofs thinking your audience is the professor or the grader. But once you pass that point, you still, if you're on the other end of the chalk, so to speak, you will want to consider writing your proofs with an eye towards who's going to be reading them. Beginning students, intermediate students, advanced students. And the more advanced your audience is, the less you need to fill in gaps. And you certainly don't need to include this unless it's all but the very basic beginning students. Okay, so it's a value judgment. In any event, we do need to say, maybe I shouldn't have made this thinking out loud, because we do need to say to start this proof, we will consider two cases or something to that effect. Okay. So case 1 is when x is bigger than or equal to 0. If x is bigger than or equal to 0, then absolute x equals x. And so this expression that we're trying to prove is equivalent to, holds if and only if this holds. In fact, essentially these are the same because we're saying that absolute x equals x. Okay. But We do know that this holds because we are under case 1, x is greater than or equal to 0. So this inequality is just the same, and this one holds because x is non-negative, therefore negative x is non-positive. Okay. So this holds, therefore this holds. Case 2 works essentially the same way with a few changes. Case 2 is x less than 0, so when x is less than 0, absolute x equals negative x. So this expression we're trying to verify is equivalent to this. It looks just like this, but you change x to negative x, so you get this. But because x is negative, that means that negative x is non-negative, actually positive, but it doesn't really matter because we only need the inequalities, not the strict inequalities. And so that means that this holds, and therefore this holds. Okay? And then a final sentence: since these two cases exhaust all of the possibilities, we've proved that 412 holds. Here's another example. If m and n are integers, exactly one of which is even, then m squared plus n squared has the form 4k plus 1 for some integer k. Now, here's the way this proof begins, and I'll elaborate on it a bit later. Since m squared plus n squared is symmetric in m and n, meaning that if you swap m and n, you'll get n squared plus m squared. It's the same value. So this is symmetric in m and n. Its value does not change if you interchange m and n. We may assume that m is even and n is odd. Therefore, we can write m equals 2i and n equals 2j plus 1 for some integers I and j. Now we just have some algebra. It follows that m squared plus n squared is equal to this, which writes this way, and then we collect things to make it easy to see that this has the desired form 4k plus 1. And that's what we say, which has the desired form 4k plus 1, where k equals I squared plus j squared plus j. Okay. Now, a remark about this comment about symmetry. There will be theorems that you come upon where the conclusion has a certain symmetry, as it does in this case. Something about m squared plus n squared is the conclusion, and m squared plus n squared has symmetry in m and n. So we don't need to, the phrase exactly one of which is even means m could be even or n could be even. We don't know which. But the point here is that because of the symmetry, it doesn't matter. So we may as well, or we are allowed to assume that it's m that's even. Because if we assume that n is even, the argument would be slightly different, but the same argument. We'd have to say m equals 2i plus 1 and n equals 2j, but the rest will work out the same way. Okay. So it is common to invoke symmetry when it's available to basically cut a proof in half. Another way that mathematicians would approach this is to say something like, first we assume that m is even and n is odd. And then once they get to here, they would then say, if m is odd and n is even, the other way around, the proof is similar, or analogous. Some might say the proof is identical, but it's not really identical. So that's okay. It's common practice to do that, but I don't think it's as clean as this way, that you mention ahead of time you don't need to do both scenarios because of the symmetry, rather than do one scenario and then afterwards say, well, we don't need to do the second one because the proof is essentially the same. If, for example, the theorem had read, show that n squared plus m cubed has this form or some other form, now we don't have the symmetry. If you swap n and m, you may in fact alter the value. In fact, you generally will alter this value. Okay. So a symmetry argument would not work in this case. Another example, let m and n be integers if m and n differ by 3, and if the product mn is less than 0, then m squared plus n squared equals 5. Here's how the proof might go. The hypothesis mn less than 0 is equivalent to the fact that m and n have opposite sign. Moreover, since the statement of the theorem remains unchanged if we interchange m and n, we can assume that m is less than 0 and n is greater than 0. I wrote this out this way just to show you one way to say this. I could have said, moreover, since m squared plus n squared is symmetric in m and n, we can assume that m is less than 0 and n is greater than 0, once we've said that they must have opposite sign. Okay. So either way would be just fine. But again, we are using a symmetry argument to cut the proof in half. So in summary, therefore, we have m less than 0, n greater than 0, and n equals m plus 3. Where did this come from? Well, you are relying on the reader to be able to sort that out, and so what is the reader going to do? If they don't see this immediately, they should go back and reread the theorem. The theorem says that m and n differ by 3. So one of them is 3 bigger than the other, but since m is negative and n is positive, n is the bigger of the two, so it is equal to m plus 3 rather than m minus 3. Okay. So you're leaving a little bit for the reader to sort out, and that's good. It's not a lot, and it gives them the opportunity to think a little bit. But note that if m is less than or equal to negative 3, then n, which is equal to m plus 3, is less than or equal to 0, which is not the case. N is greater than 0. And so m equals negative 2 or m equals negative 1. Okay. That's something you can spot from this. The m and n are tied together like with a string of length 3, and n is positive and m is negative. If m is too negative, it's going to pull n to the negative side, but n is not negative, it's positive. So that's where this, what sort of inspired this sentence. Okay. So this leaves the two possibilities. M equals negative 1, and therefore n equals 2 because of this, or m equals negative 2 and n equals 1. Life has now become simple because we have two possibilities and they're both concrete. All we have to do is plug in now. So if 1 holds, then m squared plus n squared equals negative 1 squared plus 2 squared equals 5, and if 2 holds, we also get 5. In all cases, or maybe I should have said in both cases, m squared plus n squared equals 5, which is what we wanted to show. Notice the numbering here. This is another way to number things and refer to them later. This is good when you have consecutive things that you want numbered. I could have set each one of these out in a display and put an equation number on the right here, and then referred to the equation numbers. That's equally good. You might be wondering, when should I display an equation, and when should I just leave the equation in line in the theorem, or anywhere in the proof as well? When should I display equations? When should I not display them? There's no proper answer to that, other than to say, if the equation is complex, if it's relatively long, if it's going to require some study, better to display it. Makes it easier on the reader. Short, not necessary. I could have put m squared plus n squared equals 5 at the end here, period, and it would have been fine. I like to display a little more than I need to sometimes, just also to break up the text. I don't want long sections of all inline text. I like to see the equations. It kind of gives some extra white space and can break up things a little bit, so that's helpful. But again, this is style, and there are going to be differing opinions on this. For the next example of direct proof, we need a fact, which you may already know, but just in case you don't, if k is a positive integer, then k exclamation point, this is read k factorial, is the product of the positive integers 1, 2, 3, and so on up to k. So 1 factorial is 1, 2 factorial is 1 times 2, which is 2, 3 factorial is 1 times 2 times 3, which is 6, 4 factorial is 1 times 2 times 3 times 4, which is 24. Also, 0 factorial is set to be 1 by convention. Another fact we need is this definition of the word composite. An integer that's not prime is said to be composite. Okay, let's take a look at this theorem. Let m be a positive integer. Then there exists a natural number n for which the m consecutive integers, starting at n plus 1, going up to n plus m, are composite. This is actually an important theorem. It tells us that we can find a string of consecutive composite integers as long as we want, length m. We just have to find the starting point. That tells us that there are longer and longer sections of the integers that are only composite integers, no primes, which means that the prime numbers are, in some sense, thinning out as we go farther out in the integers. As to the proof, we are being asked to find m consecutive composite integers. If m is 1, then we can take n equal to 0, we can start at 1 and end at 1, and that's composite. So we can assume that m is bigger than or equal to 2. Well, this takes a little bit of experimenting, a little bit of thinking, trying to find a key idea. But when you're doing that, it's always a good idea to think of some small cases first, sometimes that will tip you off as to what to do. How would we find two consecutive non-primes? Well, this product, 1, 2, 3, plus 2, is divisible by 2, so it's composite. 1 times 2 times 3 plus 3 is divisible by 3, so it's composite. We have two consecutive integers that are composite. 3 factorial plus 2 and 3 factorial plus 3. Already this may give you an idea what to do, but let's try one more step. If we need 3 consecutive composite integers, the pattern is already exposed here. 4 factorial plus 2, 4 factorial plus 3, 4 factorial plus 4. Each of those is divisible by a different integer, but the integer is greater than 1, so the number is composite. 4 factorial plus 2, 4 factorial plus 3, and 4 factorial plus 4. It should now be fairly clear that for any integer k greater than or equal to 2, k factorial plus 2, k factorial plus 3, all the way to k factorial plus k are consecutive composite integers. How many are there? K minus 1, because we start at 2 here and go up to k. So all we have to do is take k equal to m plus 1 to get m consecutive composite numbers. So here are the numbers, and that proves the theorem. So again, let me reiterate, because this is an important point. Sometimes the best way to approach a proof is to consider some simple cases first. So we took m equals 1, we took m equals 2, and m equals 3. And that may give you, it'd be easier to get a solution for simple cases and may give you an idea how to generalize. Let us now take a look at some theorems concerning polynomials and their roots. We have enough proof techniques to prove some theorems that are very useful. Before beginning, however, let me make a few remarks about complex numbers. You know, I don't even know when in a student's career they study complex numbers, so I'm not sure whether you as listeners to my video are familiar with complex numbers or not. And we don't need very much at all, so I'm just going to go quickly just over the couple of things. So as you may know, complex number is a number of the form z equals a plus bi, where a and b are real numbers, and where I is this mysterious number with the property that I squared equals -1. The real number a is called the real part of z, and b is called the imaginary part of z. If b is non-zero, if the imaginary part is non-zero, then z is referred to as a non-real complex number. When b is 0, of course, we just have a, and so it's a real number. So real numbers are complex numbers. Therefore, complex numbers are a generalization of real numbers. Addition of complex numbers is defined simply by adding the real parts and then adding the imaginary parts. So if we have two complex numbers we want to add, we add a plus c, that's the real parts, b plus d, the imaginary parts. Multiplication is defined by following the same distributive and commutative laws you would follow just for arithmetic of real numbers, but including the fact that I squared equals -1. So when I multiply these two complex numbers together, I would do so just as though everything was real, and then the I squared would become -1, and then when I collect the real parts, I'm going to have AC minus BD, because I squared is -1, and the imaginary parts are AD plus BC. The complex conjugate, or simply the conjugate of a complex number, is the complex number you get by changing the sign of the imaginary part. And the operation of taking a complex conjugate is well behaved with respect to both addition and multiplication. The conjugate of the sum is the sum of the conjugates, and the conjugate of a product is the product of the conjugates. Unfortunately, I'm going to have to put a space in here because the two bars look like they're touching, and that doesn't help. Okay? Finally, if p of x is a polynomial whose coefficients are complex numbers, then the complex conjugate of p of x is defined to be the polynomial formed by taking the complex conjugate of each coefficient. So it looks like that. Okay, now we're ready to proceed. First, we have a theorem. If p of x is a polynomial, and I'll write it out like this, with complex coefficients, then r is a root of p of x if and only if x minus r is a factor of p of x. This is a well-known theorem that's used all the time. So here's the proof. This is a biconditional, if and only if, so we have two things to prove. First, if x minus r is a factor of p of x, then p of x has the form x minus r times q of x, where q of x is some other polynomial for some polynomial q of x. It follows that p of r is 0. You just plug in r for x, you'll get r minus r, so you get 0. So r is a root of p of x. That was the easy direction. It's often the case, not always, but often, that a biconditional, which is composed of a statement and its converse, one direction, either the statement or the converse, will be quite easy. The other direction will be much harder. It seems to be a common theme. As to the converse, we suppose that r is a root of p of x. So p of r is 0. And we wish to show that x minus r is a factor of p of x. Well, first we note that p of x is equal to p of x minus p of r, because p of r is 0, and we can gather together the coefficients in this difference, and it looks like this. And notice the constant term has canceled, because it's the same in p of x as it is in p of r. So, if we can show that x minus r divides each of the things in parentheses, x to the k minus r to the k, for all k bigger than or equal to 1, it will follow that x minus r divides this entire sum. In other words, it divides p of x, which is what we wanted to show. So that will complete the proof. Of course, for k equals 1, this is saying x minus r divides x minus r, which is rather obvious. So we can assume that k is at least 2. It's pretty obvious for k equals 2 as well, but that's okay. The truth is that proving that x minus r divides x to the k minus r to the k is most easily done using mathematical induction. And we will do that in a later chapter. But since we haven't discussed induction, we don't have it at our disposal, spelling error, we have to find another approach. Also, it would be helpful if we had already introduced what is called summation notation. That would be somewhat helpful in the exposition, but we haven't covered that yet either, so we're going to have to be a little sneaky and work around that. These are not critical problems, but it does kind of illustrate that mathematics, one result may depend on other results, and it's not always easy to know how to organize a textbook, for example, so that you always have at your disposal whatever it is that you need. Sometimes you need something and you haven't discussed it yet, and so this is a case in point. So we begin by writing SK equals sum I plus j equals k, xi rj. And what this means for us now, in lieu of summation notation, which we don't have, as I said, this is to denote the sum of these terms, x to the I, r to the j, where I and j must be non-negative. We don't want any negative exponents, so they must range from 0 up to the maximum of k, because I plus j equals k. So we can't let either one of these go past k, because then the other one would have to be negative. Okay? So here's 4 examples that will make this hopefully crystal clear. S1 is the sum where the sum of the exponents is 1, so it's just going to be x plus r. X2, here the sum, S2, the sum I plus j equals 2, so you've got x squared plus xr plus r squared. For S3, the sum of the exponents is 3, so you've got x cubed plus x squared r plus xr squared plus r cubed. And here is S4, I'll let you look at it. So that should make it pretty clear what the S's stand for. And note that in say sk minus 1 has k terms, because the exponent of x, for example, ranges from 0 to k minus 1 in sk minus 1. And so there are k integers here from 0 to k minus 1. And each value of I uniquely determines the value of j, because I plus j has to equal k minus 1. So we can count the terms by just counting the different exponents of x. Now, here is the point. If we multiply sk minus 1 by x, what do we get? Well, what happens is that the exponents of x get increased by 1. So the sum of the two exponents, the exponent of x and the exponent of r, instead of being k minus 1, is now k. So the terms in x sk minus 1 are actually terms in sk. They belong to sk because the terms have the same form, x to a power, r to a power. It's just a question of what the sum of the exponents is. And by multiplying by x, we bumped up that sum by 1, from k minus 1 to k. So the k terms we get from this sk minus 1 all belong to sk. But sk has one more term, because it has k plus 1 terms. The term that's missing is r to the k. You're not going to get r to the k by multiplying anything by x. Okay? So that's why I had to subtract r to the k from sk in order to get x sk minus 1. And the same reasoning applies when you multiply sk minus 1 by r. But now the term that you don't get in sk is not r to the k, but it's x to the k. Well, once you've grappled with this, the rest is, as they sometimes say, trivial. If you subtract this one from this one, x sk minus 1 minus r sk minus 1, the sk's cancel, and you get x to the k minus r to the k. And so x minus r divides x to the k minus r to the k. And the proof is complete. Okay. Well, this theorem has a whole bunch of corollaries. It's very important. First corollary. If p of x is a polynomial with integral coefficients, so the coefficients are integers, then any non-zero integral root of p of x must be a divisor of the constant term a naught. Well, as to the proof, Theorem 419, the one we just proved, tells us that if r is an integral root of p of x, then x minus r is a factor, so p of x equals x minus r times q of x. So if the constant term of q of x is b naught, then by comparing constant terms on both sides, we get a naught equals negative r b naught. So r divides a naught. So this is almost an immediate consequence of Theorem 419. Also, something very useful to remember if you're looking for integer roots of a polynomial that has integer coefficients. And if, in fact, if the coefficients are rational, you can clear the denominators by multiplying by a greatest common divisor. By multiplying by the least common multiple of the denominators. And that will change the polynomial, but it won't change the roots. And so this will still apply, even if the polynomial has rational coefficients. Second corollary, if a polynomial of degree n, bigger than or equal to 1, with real or complex coefficients has a polynomial of degree n, bigger than or equal to 1, with, all I really need to say is with complex coefficients, frankly, because real numbers are complex numbers. Such a polynomial has at most n distinct roots. Well, if a polynomial p of x of degree n were to have n plus 1 distinct roots, then Theorem 419 would imply that these were all factors of p of x, and so p of x would look like this, but now we have a problem, because on this side the degree is at least n plus 1, and on this side the degree is n. So this is not possible, and therefore p of x can have at most n distinct roots. That's not actually the strongest result in this direction, but it was a direct consequence of Theorem 419. Another one, let p of x be a polynomial that has real coefficients. Then the non-real complex roots of p of x come in conjugate pairs. If z equals a plus bi as a root, then so is its conjugate. And here's the proof. If z equals a plus bi is a non-real root of p of x, then again, Theorem 419 tells us that x minus z is a factor of p of x. Now we take complex conjugates, and we get, this is the complex conjugate of p of x. On this side, we're using the properties of arithmetic and taking complex conjugates of some product, whatever. We can write this, obviously x just a variable. Z, we take its conjugate, we take the conjugate of q of x. But p of x, by assumption, has only real coefficients, so it's equal to its own conjugate, and therefore we get this equation. And therefore, when we put x equals z bar, we get 0. So z bar is also a root of p of x. Okay. These are, as I said, the Theorem 419 is important, the corollaries are important. So we've actually done some good mathematics here, and the proofs are not that difficult, really straightforward. Good proofs for you to study. If you really want to become fluid at proof writing, I would make the following suggestion, and that is go back over this material, in fact the whole chapter, and write down each theorem and try to prove it yourself. And if you get stuck, or even if you don't get stuck and finish, then go back and read the proof that's in the book and compare. This is a great way to get practice in proof techniques, or anything for that matter. Okay. Many theorems in mathematics assert the existence of some object, and these are called existence theorems. Sometimes an existence theorem can be proved by actually constructing the object that's desired in the subject of the theorem. And those proofs are called constructive proofs. But other times there doesn't seem to be any way to actually construct the object whose existence we're trying to prove. And so we need a different way, in a sense, proving that such an object exists without actually showing it. They do that sort of thing in astronomy all the time. Proof that there must be a planet revolving around a star or something because the way the star is wiggling indicates it's being affected by gravity in certain ways. They don't see the planet, but they know something's there. So that's sort of an analogous situation. And it's done also in physics, in the study of subatomic particles. We can show certain particles must exist because other particles' behavior indicates that it does. But in mathematics, this is black and white. In physics and astronomy, we don't know for sure what's going on. That probably insulted the physicists and the astronomers, so I apologize. But in mathematics, we don't have those problems. So let's look at some examples. Here's a constructive proof, and it's very simple. So, the whole point of this is to just illustrate constructive proofs. Maybe I should try to find a better example, but this will illustrate. The polynomial x cubed plus x squared minus 8x plus 4 has an integral root. Well, this is an existence theorem. This could have been read, there exists an integral root for the polynomial p of x. Corollary 422 tells us that since p of x has integral coefficients, the integral roots of p of x, should they exist, must be factors of the constant term 4. So they must be either plus or minus 1, plus or minus 2, or plus or minus 4. Incidentally, 0 is not a root. We can tell that immediately. Well, so all we have to do is check 6 numbers, plug them in, and you will find that 2 is a root, r equals 2. So we have, in a sense, constructed the root. We've constructed the object whose existence we're trying to show. Let me give you an example of a non-constructive proof that's similar in spirit. But before doing that, the proof is going to rely on a famous result known as the fundamental theorem of algebra, which we cannot prove. It's actually quite difficult. But what it implies is that any polynomial of degree at least 1, so non-constant polynomial of degree n, has n complex roots, counting multiplicities. So we must count what you might call duplicate roots. Just for example, this cubic polynomial factors like this. And so we would say it has 3 roots, but the root r equals 2 is a double root, so it gets counted twice because of the exponent 2. Okay. Theorem. This polynomial, 79x to the 113th power minus 12x to the 97th power, and so on, has a real root. Well, first of all, there is no way you're going to find that root. Okay. So you're not going to be able to construct a root and thereby show that there is a root. You could approximate the root. There are many numerical techniques such as Newton's theorem and so on, Newton's method, that will enable you to approximate a root, but you're not going to be able to construct it. You're not going to be able to find the exact value of the root. On the other hand, Corollary 424 tells us that the complex non-real roots of this being a real polynomial come in conjugate pairs. So the number of non-real roots is even. But the fundamental theorem of algebra tells us that there are 113 roots, counting multiplicity. That means one of the roots, at least, is not non-real, in other words, is real. So there is a real root of this polynomial. Okay? Even though we don't know what it is. So I want to emphasize how much, you should note how much mathematics we were able to establish, useful, important mathematics, as a more or less direct consequence of a single theorem, 419. So that clearly illustrates how mathematics builds upon itself, and should also make it clear how important it is to stick certain things, such as Theorem 419, into your toolbox. In fact, all of these should go into your toolbox, but some theorems are clearly more important than others, okay, because they can be used to easily prove others.